Welcome to 24 Hours of PASS Summit 2015 preview. We're excited you could join us today for Bill Preachuk's session, Hadoop Essentials for the SQL Server Professional. This 24 Hours of PASS event consists of 24 consecutive live webcasts delivered by expert speakers from the PASS community. This session is a preview of one of the many technical sessions that will be presented at PASS Summit in October this year. Recordings will be available in 1 week at www.24hoursofpass.com. My name is Angie Horrell. I'm from PASS HQ, so please look for me at Summit, and I'd love to meet you all. I have a few quick introduction slides before I hand over the reins to Bill Preachuk. He will speak for 40 to 45 minutes, and then we'll move on to the Q&A where you can ask him any questions you may have. Next slide, please. If you have any questions or if you're experiencing any issues, just type your question into the question pane on the GoToWebinar control panel and someone will assist you. Feel free to enter your questions in the Q&A field at any time. Once we get to the Q&A portion of the session, I'll read off your questions to Bill. And since all attendees are muted, you will need to submit questions by typing them in the Q&A field. Also, there is a short evaluation at the end of the session. Your feedback is very important to us, so please take a moment to complete it. It will appear in your web browser. Next slide, please. 24 Hours of PASS would not be possible without the support and dedication of our sponsors. They are the reason this event is available to you free of charge. I'd like to take a moment to thank our presenting sponsors, Microsoft, Dell Software, and Idera. In addition, I'd also like to thank the supporting sponsors for this event, HP, SQL Sentry, and Pyramid Analytics. Next slide. Next, I'd like to bring your attention to the upcoming PASS Summit. Taking place in Seattle, Washington from October 27th to the 30th, PASS Summit 2015 will feature over 200 sessions with world-class SQL Server experts. Planned and presented by the SQL Server community for the SQL Server community, PASS Summit is single-handedly the largest gathering of SQL Server and BI professionals in the world. With over 5,000 registrants from all over the world, PASS Summit is also a great place to network and meet face-to-face with experts, peers, and MVPs. I hear it's a lot of fun. More importantly, PASS Summit delivers on providing you with the answers to your SQL Server issues, along with the knowledge, strategies, and skills you need to stay ahead of the curve. Save $200 right now by using the discount code 24HOP15 when you register. Optimize your savings by registering before the end of Sunday, September 20th. To find out more about the PASS Summit, visit www.passsummit.com. Make sure you explore everything PASS has to offer for data professionals. You can join local user groups around the world, virtual chapters, find free online resources through our Learning Center, and read up on the latest community news in the Connector newsletter. For those interested in business analytics, check out the PASS Business Analytics Conference happening in May next year. Visit www.passbaconference.com for more information or to subscribe to our bi-weekly BA Insights newsletter. And now, please allow me to present the speaker of the hour, Bill Preachuk. Bill is employed by HurtonWorks as a systems architect. He is also SQL Server MCTS with plenty of years spent in the SQL Server DBA developer DW trenches. Bill has been in IT since 1991 and has presented at multiple SQL Saturdays along with PASS, Hadoop, Analytics user groups meetings in the Twin Cities, Wisconsin, Iowa, and Winnipeg. You can see his contact information there, and I'm going to hand it over to Bill.
Thank you very much, Angie, and thank you, PASS. Welcome, everyone, whatever time of day you may be there listening. It's a pleasure to be here. What we're going to discuss today, of course, is a 7-hour presentation boiled down to 45 minutes. What you're really going to get is a taste of Hadoop. You know, we can't go into much detail, but we're going to focus on what's really important today. And what really matters is what we're going to focus on especially is, number one, what Hadoop is. We're going to talk about storage and computation. And we're also going to focus heavily on Hive, the SQL variant that is built upon Hadoop. And we're going to have a demo, and we're going to go into a lot of the features that Hive can give you. So we're going to move along fairly briskly. I want to ensure that we get to the demo, and we should be pacing well, but we're going to move fairly quickly. I just want to let you know and to remind you that the session is being recorded, so you can always refer back to it. And please do jot down your questions and have those available, and we will answer those close to the top of the hour at about 50 minutes too. So let's get started. Here's an introduction to Hadoop. We'll cover this hopefully in about 15 minutes. We go right back to the history. Hadoop started by Google, of course. They published a couple of white papers, and one of them was called MapReduce, and the other one is about the Google file system. And what they really dealt with was methods of doing large-scale distributed parallel processing. One dealt with storage, one dealt with computation. And again, they open sourced these white papers, and Yahoo grabbed those white papers, saw the value in them, implemented the ideas within, improved on them, and open sourced the project. Interestingly enough, a large majority of that Yahoo team, they moved along and became Hortonworks. So Hadoop has a long history. Going to the Apache website for Hadoop, the definition is it provides a distributed file system called HDFS, the Hadoop distributed file system, that can store data across thousands of servers, and it also provides a means of running work, MapReduce and Yarn and Tez, across those machines, running the work near the data. That phrase, running the work near the data, you'll see is very important, and also to understand that you're dealing with tens, 20s, 50s, hundreds, even thousands of servers. Now, first we'll discuss HDFS, the Hadoop distributed file system. Now, with HDFS and a Hadoop cluster, think of many, many machines, like I said, 20, 50, 100, 1,000 commodity servers. Ideally, these would be boxes with a lot of memory, and they'll have a lot of inexpensive storage. And when we talk about that, we're talking about regular disks, JBODs. We're not looking for RAID or expensive things. You'll see why soon. You fill these machines up with memory and disk, and you'll use them in the cluster. Now, HDFS and Hadoop itself, they're not operating systems in them, on their own. They sit on top of your OS, and they sit on top of your logical file system. They sit on top of your physical file system. So, Hadoop is installed on Linux or Windows, and HDFS sits on top of your local file system. So when we're dealing with files and we're storing them into HDFS, think of it as it really is you're writing once and reading many times. Important key point is that all of your files are split into blocks of the same size. And these blocks are spread across the cluster. So pictorially, 400 megabyte file, these examples will show 5 data nodes, aka cluster nodes, but imagine there are many more. And that file is broken up into 3 files, all of 128 megabytes, plus 1 with the leftover bytes, and spread out onto separate data nodes. So, you're probably thinking, great, now we've taken a file and split it into pieces. That doesn't seem particularly reliable. Well, a key feature to HDFS is that blocks are replicated. So all of those data blocks are copied to 3 different nodes. And it is for fault tolerance, but it also provides a very strong performance boost because, again, now your data is available in 3 places instead of 1. This happens behind the scenes. You don't have to control it. It happens for you. Obviously, you can change that replication level and replicate it more or less than 3 times, but you rarely will change that. And HDFS obviously keeps track of those copies of the blocks and makes sure that their checksums and everything balances, and it can even slot them on the correct racks if you have large servers to make sure that everything's distributed. So here we have our data nodes, and the blocks have been replicated across to the nodes. So now you have 3 copies of that file sharded and sent out across the cluster and replicated. So here's where you see why we just use regular disks. We don't need RAID or other things like that because we actually, as part of HDFS, it has built-in redundancy and built-in fault tolerance. Now, as we talk about fault tolerance, imagine again, this isn't a single server machine or even 2 or 3. You're looking at dozens or hundreds of machines. And when you get into even thousands of machines, one of the problems that you have in parallel computing is that you are going to have machines fail. You know, if your computer fails for 1 day every 3 years, that means 1 in 1,000 days it's going to fail. So with 1,000 servers, you have to understand that at least 1 or 2 will be down at any given moment. With HDFS and with Hadoop, node failures, data node failures, are expected. So the cluster itself will look for a failed node. It will go through and it will find a missing or under-replicated block. It can tell whether a node is available, and it will re-replicate the data to make sure that we maintain that 3-copy protection level and your data is safe. So for whatever reason, if data node 2, as we see in the picture, if data node 2 becomes unavailable, could be unplugged, could be someone stole it, could be a catastrophic failure, or it just needs to reboot. If that becomes unreachable, those specific blocks 2, 3, and 4, are replicated from other copies of the blocks to other data nodes, again, to maintain that 3-copy protection level. Now you may be wondering, how does Hadoop know, if that block has been corrupted? How does it know if a block's not available? And again, how can this cluster on whether a data node has failed or is unreachable? There's some intelligence involved here. So with that in mind, a key concept and a key server, in a Hadoop cluster is known as the name node. Now, we spoke briefly about each of these data nodes being commodity hardware, commodity disks, very simple machines, they're designed to be replaced. This name node is not that. This is a very critical, high performance machine. This is a machine that can't go down. In every installation now, you're having a primary and a standby name node. The secondary name node is available, and what the name node does is that it stores all the metadata of your cluster, right? So it knows what files are in the cluster. It knows what blocks constitute those files, where those blocks and where the block replicas are, and it coordinates the work of finding out if blocks are missing, if data nodes are unavailable, and it has the intelligence, and with all of that metadata, it is the key to being able to re-replicate all of that data. So it's a very important machine and of high value to your cluster. So at a very high level, this is the storage component of Hadoop, HDFS. So let's transition in, and let's now talk about MapReduce, Yarn, and Tez, the compute and the processing portion of Hadoop. We go back to our definition again. This is a means of running work across the machines, running the work near the data. We'll introduce Yarn. Yarn is the data operating system. So it handles all of the concepts of resource management and job scheduling within your cluster. Logically, it sits on top of or above the file system, and it's the interface between processing engines like MapReduce, which is the old original processing engine, and other interactive engines such as Tez. And basically, it's that interrogator resource manager. Now, when we're talking about processing jobs in a cluster like Hadoop, there's really 2 ways to look at it. We think about it in a macro level or in a micro level. Now, at a macro level, we're thinking about, across these 20, 50, 100 nodes, how do jobs run across the cluster, right? And then at a micro level, we're thinking about, on a specific data node, how does a particular task run on that specific data node? So it's easiest to think about it if we think at the macro level first. So briefly, let's discuss how Hadoop runs a job. Now we'll introduce a couple, new servers there's a global server called the Resource Manager. Again, this is a high availability server that handles that scheduling and resource management. And then on each of the data nodes, you'll note that we have the Node Manager, that coordinates all of the processing on each data node. So when you, the client, have a job that needs to be done, a query, the query requests that of the Resource Manager, which talks to the name node, and the name node, high performance metadata, tells the Resource Manager which blocks constitute that store sales file and which blocks on the cluster should be used. So armed with that information, knowing what blocks are needed and where they are, the Resource Manager spawns off a process called the Application Master. And as you can see, it puts that application processing logic, the master control, inside the cluster. So when you think about it, when you have multiple processes happening, you can have multiple application masters distributed across the cluster. So again, you're sharing your resources very carefully and effectively. And that application master, knowing where all of the specific blocks are that are required, spins up lightweight containers on each of the nodes. These are little Java virtual machines that might have approximately 4 gig of memory and their own disk allocations. And each of those containers are assigned to do work for that task. Now you'll note very importantly that all of your processing is happening local to the data, and that's critical. You're not bringing terabytes of data across the network to process. Instead, you're bringing your processing to the data nodes. You're bringing your processing to where the data is stored locally. And again, this is a simple example, but imagine this across hundreds of nodes with hundreds of thousands or millions of blocks. And you can see the fan-out effect of this kind of processing. So anyways, as each of these containers run, and once they're finished, they signal to the application master that they're done, and it sends the information back to the Resource Manager and back to you, and you have the data that you required. So interestingly enough as well, HDFS, has that built-in redundancy and that fault tolerance, where blocks can be replicated. MapReduce, Yarn, and Tez has that same type of fault tolerance. If a container fails, the application master can actually spawn off another container and have it reprocess the job. And if a block is unavailable, it can even put that container on another data node and rerun the processing that was missed. So again, one failed container will not fail or cause 1,000 other containers worth of work to be thrown away. So again, at a cluster-wide level, there's an impressive amount of fault tolerance in Hadoop. Now, let's talk again, going down to the micro level. How does a task run on a particular data node? You have those containers, they're executing, and they're processing those blocks. Well, this is where MapReduce comes. This was the original processing engine on Hadoop. Now, MapReduce, going back to the original paper, really breaks a large problem into small sub-solutions. You have processes called mappers and reducers. And really the mapping is reading data, through the block line by line, applying a process against it, and then taking that data, shuffling and sorting it, and then sending it off to a reducer process, which aggregates and consolidates and does additional processing to the data. And what the MapReduce original paper, white paper, realized or posited correctly is that just about any kind of processing in a parallel environment can be broken down into steps of mapping and reducing at a high level. So, using some SQL analogies, a map is really like your select and your from and your where. This is where you're going through and parsing through a lot of data. You're trying to find specific values. You're taking certain columns worth of data. I did air quotes like that, but of course you couldn't see me. This is where you're doing your froms and your wheres. You're applying a simple filter to it. And then once the mapped data, you've selected some data that gets sent along to a reduce phase, that's where your idea of aggregates comes in. That's when you're grouping data, you're taking a halving, you're aggregating the data, you're putting it into a smaller subset. That's what a reduce phase does. So another thing too about as data is passed around in a MapReduce phase, everything is sent in a key value pair data structure. So a map reads key value pairs from your source data in the blocks. It processes and creates key value pairs, which are read by the reducer, and it creates key value pairs again. So again, you'll have successive phases of maps and reduces, or in parallel. So at this point, you've had a very brief, but hopefully effective introduction to what Hadoop is at a high level. You know, the computation, HDFS, and the storage, MapReduce, Yarn, and Tez. Now, based upon that foundation, right, of, you know, HDFS, MapReduce, and Tez, what came about was the Hadoop ecosystem. Remember, this was open source processing, and people did find that it was hard to write MapReduce code. You know, it was originally created in Java, and so you're writing a lot of Java to process your data. So some of the applications built against this foundation were tools like Pig and Scoop and Hive, and these were really higher level abstractions which allowed you to use cleaner programming languages to create MapReduce jobs. Hive, for example, we'll talk in a few minutes, uses SQL, and you can write SQL syntax that creates MapReduce or Tez jobs underneath. And again, through the open source community, as people started to use Hadoop more and more of these great ecosystem applications began. You know, like I said, things like Pig, which is really good for data cleansing and data scrubbing. NoSQL databases like HBase were built on HDFS. Streaming, like Storm and Kafka, you've probably heard of some of these things. And we're not going to deal with them in this session. There just isn't enough time. But just to introduce the idea, schedulers like Uzi, pipelining like Falcon, where you can have data lineage, you know, Flume, where you can read log data in very easily, and Scoop, where you can take RDBMS or any kind of ODBC, JDBC connection and bring that data into your cluster. All of these applications built up in open source, and, you know, truly the best kind of filtered to the top, and they became put together, and then they became obviously put into a distribution and packaged up for sale and with support. Now, when you purchase or when you install Hadoop and have it as a, you know, we'll look at the Microsoft offerings, for example, you have many options of how you want to build out your cluster, and we'll deal with these quickly. Your on-premises option, we'll deal with those first. You have the bare metal install, right? You can have HDP, which is the Hortonworks data platform. That can be installed natively on Windows servers or Linux servers, most commonly Linux, but working with Microsoft, you know, Hortonworks has done a lot, Microsoft and Hortonworks have done a lot of partner work to ensure that there's a fully functional Windows version with PowerShell, you know, with C#, you know, where you can do all of your work with Hortonworks on Windows. This is where you're installing your servers, you have full power over everything. Another interesting way of running Hadoop is on your APS box, your parallel data warehouse. It comes with, or can be turnkey, with an internal Hadoop cluster right inside of your APS appliance. Very powerful, and what's interesting is it also, you know, APS, either it's there or it's coming, where they're going to have federated, you know, your PDW queries, your SQL queries, will be essentially federated with Hadoop, where you can be looking at tables and constructs inside of Hadoop, any kind of data, and you can read that essentially as an external table within your SQL query. And they're working very hard, I know, at optimizations on that, and this is a very compelling thing. It adds a lot of power to your APS box. And when you look at the power that, you know, Parallel Data Warehouse APS comes with, I have a hard time not calling it Parallel Data Warehouse, I apologize. Very compelling option. Now, you obviously have cloud options for Hadoop as well. HD Insight, that is the Microsoft Azure Hadoop as a Service option. And this is where you are able to spin up in the cloud, Hadoop clusters. Honestly, however big a cluster you want, you're looking at about 20 minutes to spin it up and have it running. You get that awesome elasticity. And one interesting feature about HD Insight is most times you're going to swap out that HDFS disk layer that we discussed, and you're going to use Azure Blob Storage instead as your layer. May seem odd, but when you think about it, Azure Blob Storage brings with it a lot of the same type of redundancies and the same type of availability as HDFS. So you're getting a lot of simplicity and elasticity in that way, and you are honestly getting the benefit of really, really cheap, in the good way, Azure storage. Anybody who's done Azure work, it's impressive how inexpensive that storage is. So, and then really another final option for a Hadoop cluster is to build out VMs in Azure. Again, as most of us are aware, really any kind of server environment now can be spun up in the cloud. You can build out your Azure VMs, and they've done a lot of work, Microsoft has, in making that easy for you. So if you've got an existing Azure environment and you've already got money to spend, you can build that out yourself and have all of that power and capability. So moving right along at a pretty brief clip, we seem to be right on schedule. We're going to talk about Hive right now. Many of you may have heard of Hive, but really what Hive is it gives you the ability to use SQL queries and SQL query language to query and report against data inside of your Hadoop data warehouse, right? It provides a mechanism, reading from the description. You project structure onto your data and you query the data using a SQL-like language called HiveQL. Now, for most everybody on this call, we're all SQL Server people. Hive is your entry level into Hadoop. Myself included, when you start using Hadoop, if you haven't already done so, you will almost assuredly be using Hive. Everyone speaks SQL, and it's a very impressive implementation of really a SQL language and what you can do with it. And we'll have a demo in a few minutes where we'll show a lot of the capabilities. Now, inside of Hive, you're defining tables, which are really views, upon your files in HDFS. So you're putting a SQL structure on it. Now, when you execute a DDL or change it, you're not changing any of the underlying file. The files stay there, they remain, and you're projecting SQL on top of it. Now, we'll introduce an ecosystem application called HCatalog. That is a global metadata layer. When you think of having a Hadoop cluster, you've got all kinds of files and data of all different types, massive volumes of data, and you don't want to have people redefining the metadata. So HCatalog is that one place to have a single structural definition for a table or a file or any kind of information inside of Hadoop. So when you create a Hive query using HiveQL, you're using HCatalog to get that metadata, which gives you the structure and then allows Hive to create a query and to write underlying jobs that will access the data in the Hadoop distributed file system. So, as mentioned at the bottom here too, each of your tables that you're defining maps to a directory. And we'll see the significance of this in our demo very soon. Architecturally, there are differences between SQL Server and Hive. And in the large Past Summit presentation, we'll go into a lot of detail on this. With SQL Server, you have data pages, right? All of your data comes into a particular format of a data page, and as well, you have an entire database, hundreds, perhaps even thousands of tables mapping to one MDF LDF file. And that's going to be on one server, perhaps two, right? If you've got your always-on cluster. It's, very strongly supported with indexes and views, stored procs and everything, right? Hive kind of turns that on its head. You're dealing with a parallel environment. Everything is files. and remember it's these sharded files into blocks, right? You can have many different types of file formats, text, CSV, more intelligent formats like ORC, right? That's very variable. And in Hive, you don't have as many supporting objects. Things like indexes, you don't have that same concept of an index when you're dealing with this fan-out parallel processing. And importantly, again, when you define a table, you're mapping it to a directory which can have many, many files. And if you remember anything, though, of the differences between SQL Server and Hive, SQL Server is schema on write, Hive is schema on read. So you have to take your data in SQL Server and bring it into, or your data, bring it into SQL Server and fit it into the schema that you're defining. Any changes to that data or to that schema means changes to the underlying data. With Hive, you're taking your file and you're defining a schema on top of it as you read. And again, in terms of parallelism, Hive and HDFS and MapReduce, Tez, Yarn allows you to scale to petabytes. There are multi-petabyte data warehouses, hundreds of petabytes even, running off of Hive. Whereas SQL Server, incredibly powerful, though you do find, in my opinion, once you get past that terabyte, you're doing a lot of hard work with a single server environment to keep that performance the way you want it to be. Now, HiveQL, the SQL language that you find in Hive, they've worked very hard, the Hive community, to bring it up to very close compatibility, really to all the RDBMSs, but very much so to SQL Server. A lot of good people at Microsoft have worked hard on this as well, and very little of what you find in T-SQL isn't found in Hive. So at a query level, it's all there, and over time it just continues to improve. I say this many times, but the pace of speed of introduction of, well, that's a lot of words, basically the changes to Hive happen so fast and they're so dramatic right now because it's still so new. I liken it to moving from SQL 6.5 to SQL 7 to SQL 2000, where you come up with a new version and you go, whoa, what just hit me, right? Where your queries will be an order of magnitude faster without changes. Those are the types of things we're seeing in Hive. And it's very powerful, but to this day, you have a much quicker release cycle. Now, we talked about our execution engines, MapReduce and Tez. This is just a quick representation of the differences. On our left, we see MapReduce, and it was designed, again, for stability, right? It was designed for very large data processing and for, the processing to not fail, right? So in between maps and reduce, quite often, the data will be written to disk. And then when the next map starts again, it'll reread from disk. Very time intensive, very labor intensive, right? This is the old faithful app. Now Tez and Yarn, these were rewrites, essentially understanding that, Hadoop had to get away from a very batch method of processing and be much more real-time oriented. So Tez brings in a lot of concepts like in-memory processing, caching. Tez does not spill data to disk unless it really has to, so it is much more performant, and it allows for much more, improvements like vectorization and things like that, where you can really get dramatic query performance improvement. Well, we're right on time, and we'll be able to spend a good amount of time on this demo now, which I'm very glad. Now, I used my skills of an artist to put together this representation of our demo, and we'll just go over it for a quick second, what I'd like to show you. What we're going to do is I've taken two data sets from the web and just did a quick parsing and just an idea. One data set is median household incomes by zip code. So they're about 15 years old, but it's really interesting because by every zip code in the country, we have their median household incomes. Useful information. And the file on the right is Medicare volumes by zip code. So for particular hospitals at a particular zip code and city and the hospital name, it tracks specific medical procedures that were done under Medicare and how many were done, right? So As you'll notice, it's a little hard to see, but the file on the left is pipe delimited. The file on the right is tilde delimited. And you'll notice as well that the file on the left has 2 lines of metadata at the top, right? Column names and some column metadata, GeoID, geography identifier, right? Something to note of as we do our processing. So in our demo, we're going to take this data, bring it into Hadoop, and then we're going to define our Hive schema upon it. We're going to run some Hive queries, and then we're going to add some more data, and we're going to see the significance of adding that more data. And then we're going to run some more Hive queries. And we're also going to introduce you to the Mbari view for Hive. So let's get started. Now, I'm going to bring up my environment here. On the left, we will have our HDFS commands, where we'll be accessing the system. And on the right, we have Hive. So let's get those 2 files, and let's put them into Hadoop. So we will be doing this Hadoop fs put command, and everything just goes into a folder. So we're putting our first file into ELT sources income in the income folder, and our second folder or file into a Medicare folder, right? Medicare volume.csv, household income.txt. So there they are, and let's do another Hadoop fs, Hadoop file system command, right? And let's see what's there. We're going to do a recursive listing on the ELT sources directory. You'll see now in Hadoop, we have added in the income folder our household income, and in the Medicare folder, our Medicare volumes. Now, let's move into Hive. We're going to create our database, and then we're going to use our database. Very similar commands as we see in SQL Server. Again, you will find Hive very forgiving. And now here's where we're going to define our schema. We're going to define external tables on top of the file. So let's look really quickly at this. The highlighted text here. We're dropping a table if it exists, and we're creating our household income table. Now notice that we've got char, data types, integers, column names. Looks just like a regular table, doesn't it? We add a few more features in here. Row format delimited, fields terminated by pipe. We have to tell Hive what the field delimiter is. We tell it what directory the data is in. Notice we didn't specify the file name, we specify the directory. And we have an interesting thing like our table properties, where we literally say skip header line count is 2. Now remember, we had these first 2 lines of junk. We don't want those to be data rows, do we? So we're going to skip them. So let's run that right now. We just defined it. And let's do that for the Medicare table again. Notice that it's tilde delimited, right? And notice that it's in a different location. Now at this point, we've created our metadata, and we will start writing some queries and running some queries. But rather than just on the command line, I want to quickly show you as well. This is a tool called Mbari. It's an ecosystem tool. And this is the dashboard for your Hadoop cluster. So you see ecosystem applications. Over on the right here, we have a Hive window. And we've got one brought up right here, where we've got an existing query here. And it looks just like SQL Server. You have your Database Explorer. You can look at databases, right? You can execute your query, right? And it's processing right now. Here's our info. And it gives you a really nice ability to run queries. So it gives you a running timeline. Now there's a little overhead with running your first query because you're opening up a Tez session, but here's our results. You know, in Kentucky, at this particular zip code, this diagnosis, this process was done 658 times, and the median household income in that part of the world is $8,500 a year. So here's the data and our results. And to really quickly show you here, gives you a lot of options in terms of tracking what was done. When we click on the Tez button over here, we can see DAG details. DAG means directed acyclic graph. This is how a map in a reduce phase gets implemented, right? And here we have information about all of our counters. These are things that you can look at here. In file bytes read, tasks launched, and then, this is really pretty, we have a graphical view where we see all of our mappers and all of our reducers that were processed, right? Including how we read the data, how we outputted the data, and then even nicer than that, we have a graphical explain of all of our maps and reduces, where we can literally see the tables that we're scanning, the filters and expressions that are running. You know, this newest version of MBARI has a lot of flexibility and a lot of power built into it. What I'm running right now, by the way, is the Hortonworks MBARI sandbox. And you can download this from Hortonworks. You can also use it. It's available in Azure. You know, you can run an HD Insight sandbox. You know, so this is a download that you can run in Hyper-V or in VMware. No problems at all. So I just wanted to let you know of this. So let's get back to old school, right? We're going to run our queries the old-fashioned way, because this does give us more information about what we're doing here. So let's run a few more queries. You know, here's a query that we're running on a non-startable join. We're joining the Medicare volume table to the household income table, and we're a string and a substring. Now in SQL Server, this would hurt you really badly, but we're going to show you what it can do in Hive. Now notice that we're selecting from two tables, and we're grouping and we're ordering by, right? Which corresponds to two maps and two reduces, doesn't it? So let's paste that code in and run it. So again, our Tez session was closed. There was a little bit of overhead the first time starting up your session, and now we're running. And this is the representation here. Your jobs run from pending to running to completed. You'll see there succeeded. We ran in 9 seconds, and there's similar results, right? So when we looked at by a particular state and zip codes, how many procedures were done, right? So it's less about the data that we're returning and more about watching the processing happen. So let's run another query again. We're going to sum up some procedures for specific states. You know, I'm from the Midwest, so we picked the Midwest, right? So here we are, and we're going to use these results in the rest of our demo and show you this. So here it is running. Just about done. There it is. So Nebraska, we'll see here, highlighted. Nebraska had this median income average and 1,611 procedures done. Now let's show some of the concept of schema on read. We're going to add some more Medicare data, right? So if we go back again, we look at our Medicare folder. Remember, we have one file, Medicare volume CSV, and it's 27 meg, right? Now we're going to put another copy of that file in there, and we're going to give it a slightly different name. And we're going to copy that into our cluster, right? And now we're going to look, and now you see we have two files that are available in that. And now there's 54 megabytes of data. So let's rerun that query again. And let's see what happened. Remember, Nebraska, 1,611 procedures. As we watch it finish. Now Nebraska has 3,222 procedures. By doubling the files, we've doubled the data. We just did ELT, but we didn't have to do any processing. We didn't have to do any effort. By dropping a file in a directory that you've defined a Hive structure upon, you have that data available to you. Schema on read. Now imagine this with files where you have hundreds of gigabytes or even terabyte a day. The amount of ETL that you would normally have to do. Instead, now you can use that schema on read capability and use the power of the cluster to force through all of that data. So that's my Hive demo. Hopefully that was helpful. Let's go back into our presentation. We're just wrapping up. We're right on time. Just a few more slides. Now to kind of wrap up what we've talked about, what makes Hadoop compelling? With Hadoop, as you can see, the way it stores data, the way it processes data, you really do get near linear scalability. If you have 10 nodes and a job runs for 2 minutes, by moving to 20 nodes and balancing that cluster, that same job will run in half the amount of time, or you could do double the amount of volume in that same amount of time, really. And as well, with this idea of sending your processing to the data, you get huge parallelism and minimal network traffic. Remember, we're not sending the data to the processing, we're sending the processing to the data. And as we saw in our demo, schema on read, what we saw in Hive, but really other tools as well like Pig and many other ecosystem tools that you can use in Hadoop, gives you extremely fast ELT. And what's really interesting as well in Hadoop is that you can have multiple workloads for a same data source. That data that we brought in doesn't have to just be used by Hive. It can be used by Pig. It can be used by Spark, other engines, other processing. So again, very powerful. And as we close up here, here's a pictorial representation. This is a real project where ETL offload, really replacing a very expensive ETL system. They went through and benchmarked on 5 nodes in blue, 10 nodes in red, and then purple was 20 nodes. These were physical boxes benchmarking performance, right? And then given that change in performance, they were able to extrapolate down, and it turned out to be true what the processing would take in 60 nodes. And with a 60-node Hadoop cluster, this company was able to get their ETL processing down to 8 minutes and 27 seconds, which essentially matched the same amount as the expensive ETL subsystem, but it was less than half the cost. And what this doesn't tell you as well, though, is that now that company has a full Hadoop cluster as well. And given 60 nodes, that probably means that they've got, I would suspect at least 200 terabytes of usable 3-copy storage like that. So again, very compelling. And a use case that you would probably look at would be data archival or EDW offload. So at this point, we've rifled through the presentation. I hope this has been good pacing for you. Angie, are there any questions?
There are a few questions, actually.
I'd assume there would be. Yeah.
Not a ton, so that's good. So one fellow asked, if you're running Hadoop on just one box rather than a cluster, why is it still so much faster at certain operations? I think this is true, isn't it?
Yeah, very interesting. Let me actually talk about that. My machine here is a 16 gig. It's a Mac. I know when I get to past Summit, it's going to be a PC, trust me. It's a 16 gig Mac with an SSD. And again, it's just one, it's multiple cores in parallel, but it still is just one machine and one node. And really that SSD gives me really good performance. There's a certain point, where, for example, when you look at the layout of a cluster, you're really looking at about 10 nodes when you think of having to have two name nodes and then data nodes as well, where you're really going to get that benefit of having that parallelism. But yeah, one thing that's happened with Hive in particular, with things like Tez, there's so much optimizations that's been going on that even with one node, it becomes so much faster. Again, to quickly sum up, these demos that I had, oftentimes I'll do more demos, and it used to take 30 seconds for a particular thing, and I would tune it, and it would go down to about 4 seconds. Well, now with recent improvements that they've done to Hive, that original 30 seconds now only takes 9 seconds. So I can't even show that amount of improvement. So, between the way you size your cluster and the improvements that's happening to Hadoop and the ecosystem tools, you still get good performance with this, what we call a sandbox. And everything is on the sandbox, by the way, that you can install in production in a large cluster. So the nice part about it is what you build, you can deploy. I hope that answered the question.
All right, we've got another one. He's actually asked a two-part question, or two questions here. If one is a SQL DB developer and BI developer, then what opportunities are there for him to move to Hadoop technology?
Absolutely. Yeah, that's one thing I'd love to talk about. We'll talk about that at the summit. Really, a DBA, there's a really good path for just about anybody in IT into Hadoop. You have Hadoop administrators. I was a DBA data warehouse person. And as you can see in Hive, Hive really has there's a data design and a data warehousing type of design. DBAs fit in very well. You really need a DBA type person to administer a large Hive installation. And in terms of development, there's data development, like a T-SQL developer, where you're doing a lot of data munging with Hive and Pig, and bringing data in with Scoop. And there's also, that pure programmer development in Hadoop. Most of Hadoop is built in Java, but you also have Scala and Scalding and Spark, and as well the Windows installations, C# and PowerShell. So there is that customization, where you'll be writing all of those apps. And then pure administrators, a Windows or a Linux administrator, they fit in as well administering the system. Really a cluster is a rack of servers. So truth be told, there's a lot of commonality between existing IT roles and the Hadoop world, but honestly, in my opinion, a SQL person has the easiest time breaking into Hadoop because Hive is such an easy, even translation. Obviously, understanding the architecture of Hadoop, makes your Hive queries better, but you're going to be able to run Hive queries pretty much as soon as you hit the ground.
All right, we've also got, can Hadoop be used from a reporting tool to prepare reports, i.e. can I develop reports in SSRS using Hadoop as data source backend?
Yes. Yes, you can. Truth be told, this is a parallel processing environment. You are not going to get as fast a response time as, a properly tuned SSAS cube or a SQL Server database that's hugely indexed. For ad hoc type processing and querying, knowing you're going to stick Hadoop cluster, it might take 10 seconds or a minute. And that's, for people who understand, that's acceptable. Many times as well, if you need that super fast access time, it'll either get, Hadoop is the long-term archival source, and it'll get put into, a small, dimensional data warehouse in SQL Server, or a NoSQL-like solution like HBase and Phoenix would be used that would give you that quick random access. But yes, you definitely can hook up SSRS, or really Microsoft and Hortonworks have the full ODBC connectivity, and as well your Excel spreadsheets. You can connect in and use Hadoop as a data source as well. But just a warning, it's going to be slower than a traditional relational database.
Okay, we've got a few more here. Is there a notion of a unique index, or do you have to manage not uploading dupes manually?
In Hadoop, you really are managing that yourself. In Hive, you can define tables with a unique index, and you can do that type of processing. But, again, with that schema on read, you're really responsible for that. So whenever there's any type of ETL, most times, kind of like in a data warehouse world, you'll often have in a data warehouse, you'll remove all of the constraints, right? All of the foreign keys and things like that, and you'll do your ETL processing and re-add them, or you will just logically, be responsible for your fact and dimension tables, referential integrity. Hadoop is the same way. You'll have your stages of processing, really your SSIS-like processing, and yeah, you are responsible for that. You can do it, and there are tools that will help you do it, but you have to take it as your responsibility.
All right, and we probably have a couple minutes just for one more question. What do we need to do to get started, and what resources are available for us to learn?
Oh, that's a wonderful softball question. I'm so happy. That must have been one of my friends. No, that's a great question. What I always like to say is it's called the sandbox. At hortonworks.com, and as well in Azure, you can, through Microsoft and HD Insight, you can basically, the demos I gave you were done on the sandbox. It is a VM image that VM Player or VMware Fusion or Hyper-V you can use to have a fully functional, and it runs on any type of computer system. And there you can run that. There's training, plenty of training, through Hortonworks and through other third-party people. But really, the sandbox has a whole bunch of tutorials. Whether it's the HD Insight sandbox or the Hortonworks one, where you can literally step through all of these pieces. And really, it is good just to kind of jump in. And another thing I would recommend is, if you can, really create a little proof of concept. I really would recommend any type of SQL person to consider some type of an archival project. If you've got some data, terabytes of data, or a massive set of data that you really can't work with on your SQL Server box, or very hard to query, and you just like to get it off of there and be able to use it, AR type data is a good example. And you can take that and bring it into even a small sandbox and work with it and show people what Hadoop can do. That's a really good way, playing with real data. There are also third-party learning companies as well that have very good Hadoop type classes and Hive and learning and things like that. So between Microsoft and the people like Cindy Gross and the Hortonworks blog, there's a lot of availability out there. And otherwise, feel free to tweet me. I'd be glad to get you some information specifically. Personally, I'd be more than glad to help.
Great. I think that wraps up the questions. So I'd like to thank you all for attending Hadoop Essentials for the SQL Server Professional. If you can advance the slides, Bill.
Thank you.
Do you like what you've heard? Bill will be presenting at PASS Summit 2015, just coming up in a few short weeks. His pre-con session, Hadoop Essentials for the SQL Server Professional. You'll have 7 hours to really dive into this. That'd be a great learning experience. You can use discount code 24HOP15 to save $200, and there's some contact information for Bill there as well. So again, thank you for attending Hadoop Essentials for SQL Server Professional. I'd like to thank Bill for his time and his expertise. Again, I'd also like to thank our presenting sponsors, Microsoft, Idera, and Dell Software, and our supporting sponsors, Pyramid Analytics, SQL Sentry, and HP. We hope you enjoyed this session as much as I did. Follow along on social media with @PASS24HOP and share your thoughts on the event with hashtags PASS24HOP and hashtag SQLPass. Stay tuned.
Thank you all for attending.
Yes, thank you, Bill. So stay tuned. Coming up next, you will find the next session, Finding Your Balance, BI in the Cloud, On Premises, or Both, with Joey D'Antoni, happening in just a few minutes.